What if the Big Bang wasn't the beginning but a rebirth? What if our entire 93 billion light-year observable universe is just a single object inside a much larger, older cosmos? This isn't science fiction, it's a possibility being explored by theoretical physicists, challenging our most fundamental understanding of existence. The clues might be hidden in plain sight, in the behavior of black holes and the baffling arrangement of the most distant galaxies spotted by the JWST. Let's explore this mind-bending possibility together. The standard Big Bang model. So, how did we arrive at our current picture of the universe? The story most of us know is the standard model of cosmology, first mathematically conceptualized by the Belgian priest and physicist Georges Lemaitre in 1927. It states that our universe exploded into being 13.8 billion years ago from a point of extreme density. From this intensely hot state, space itself began to expand. Over billions of years, gravity sculpted this expanding cosmos, pulling matter together to form the vast, web-like structure of galaxies we observe today. This model is incredibly successful. It explains the faint afterglow of the Big Bang, the cosmic microwave background, and it accounts for the accelerating expansion of the universe. This acceleration, confirmed in 1998, is often attributed to dark energy, which makes up about 68% of the universe. When combined with dark matter, at around 27%, it appears 95% of our cosmos is made of stuff we can't see or understand. This means that all the stars, planets, and galaxies we can observe make up a mere 5% of reality. The bottom line is the standard model, for all its successes, leaves us with the biggest questions in science completely unanswered. The black hole universe theory. What if there's a more elegant explanation, one that doesn't require inventing new particles or mysterious forces? A radical alternative, championed by physicist Nikodem Poplawski, proposes that our universe was born inside a black hole within a much larger parent universe. This idea flips our perspective on cosmic origins entirely. Instead of a singularity appearing from nothing, the theory suggests a physical process, the gravitational collapse of matter in a parent universe. Think of it like a star many times the mass of our sun collapsing to form a black hole, but on a cosmic scale. In this model, what we perceive as the Big Bang was actually the moment our universe formed inside that parent black hole. This framework elegantly resolves the issue of what came before the Big Bang, as the parent universe provides a clear preceding state. This cyclical model redefines our cosmic address, demoting our entire universe from everything that is to just one bubble in a potentially infinite cosmic foam. It also provides a physical source for the energy and matter in our universe, sourcing it directly from a pre-existing parent cosmos. In essence, the matter that makes up you, me, and the stars didn't appear from nothing, but was recycled from a previous cosmic iteration. Quantum mechanics and degeneracy pressure. Here's where things get really interesting, and it hinges on a core principle of quantum mechanics. Have you ever wondered what stops a dead star from collapsing forever? The answer lies in a rule established by the brilliant Austrian physicist Wolfgang Pauli. His exclusion principle states that identical particles, like electrons, cannot occupy the exact same quantum state at the same time. When gravity tries to crush matter into an incredibly small space, this principle creates a powerful outward push known as degeneracy pressure. The more you squeeze, the harder the particles push back. This is the force that supports white dwarfs against collapse, where matter is packed to a density of over 1 million kilograms per cubic centimeter. In even more extreme objects like neutron stars, the pressure is even greater, holding up against densities of over 100 trillion kilograms per cubic centimeter. This pressure is fundamentally different from thermal pressure, which supports a star like our sun, as it doesn't depend on temperature at all. Proponents of the black hole universe theory argue that this same quantum pressure could operate on the scale of an entire collapsing universe, offering a mechanism to avoid the infinite singularity. The bounce mechanism. So, if a universe collapses, what happens when this quantum pressure kicks in? Instead of crushing down to an infinite point, a singularity where physics breaks down, the collapse could halt and rebound. This is the Big Bounce, a concept heavily explored in loop quantum cosmology by physicists like Martin Bojewald. In this scenario, as the matter of a parent universe collapses, it approaches the theoretical maximum density allowed by physics, known as the Planck density, which is about 5.1 times 10 to the 96th kilograms per cubic meter. At this point, quantum gravity effects become so powerful, they overwhelm everything else. This force stops the collapse in its tracks and triggers a massive, explosive rebound. This rebound event would be incredibly brief but unfathomably violent, essentially resetting the cosmic clock for the new universe. To any observer inside this newly expanding region, that rebound would look and feel exactly like a Big Bang, while potentially preserving information from the prior cosmic cycle. This bounce also offers a potential solution to the black hole information loss paradox, a major conflict between general relativity and quantum mechanics. The paradox questions what happens to the information about matter that falls into a black hole if the black hole evaporates. A bounce mechanism suggests this information isn't destroyed but is instead carried through the rebound event into the new universe, preserving the fundamental laws of physics. Evidence from early galaxies. This might all sound like fascinating speculation, but where's the evidence? It might be hiding in the deepest images of our universe captured by the James Webb Space Telescope. According to the Standard Model, galaxies should build up gradually. Yet JWST is finding galaxies that are bafflingly massive and mature. For instance, the GLASS JWST Early Release Science Program, involving astronomers like Rohan Naidu, has identified galaxies like GLASS Z12 at a redshift of 12, meaning we see them as they were just 350 million years after the Big Bang. These galaxies are already 1 billion times the mass of our Sun, far larger than our models predicted was possible so early on. Furthermore, these ancient galaxies appear to host supermassive black holes that are millions of times the Sun's mass, a phenomenon that standard models struggle to explain so soon after the Big Bang. The Big Bounce model, however, offers a potential explanation, suggesting these black holes could be relics that survived from the previous cosmic era, acting as gravitational seeds. Galaxy rotation mystery. Now for another cosmic puzzle that might point to the same conclusion. In a random and uniform universe, you would expect galaxies to be spinning in all different directions, with a roughly 50-50 split between clockwise and counterclockwise rotations. But that's not what we see. A 2020 study analyzing over 200,000 spiral galaxies, led by computational astronomer Lior Shamir, found a significant imbalance. There appears to be a preferred direction of spin and alignment across vast stretches of the cosmos. The statistical probability of this asymmetry happening by chance is less than 1 in a billion. This unexpected alignment, observed across a scale of billions of light years, implies that processes during the formation of the universe were not as random as we thought. This large-scale pattern challenges the long-held assumption that the universe is the same in all directions, a principle that underpins virtually all of our cosmological calculations. This isn't a small, localized effect. The pattern of this cosmic spin is coherent across billions of light years. Shamir's analysis shows the distribution of spin directions fits a dipolar pattern, meaning it has a distinct north and south pole just like a spinning magnet or planet. Such a large-scale coherent structure is extremely difficult to generate after the Big Bang and points instead to a fundamental property imprinted on the universe at its very creation. Schwarzschild cosmology. So, this idea of a universe inside a black hole isn't, entirely new. It actually falls under a concept known as Schwarzschild cosmology. The name comes from Carl Schwarzschild, who, way back in 1916, found the first exact solution to Einstein's field equations, describing the spacetime around a spherical mass, what we now call a black hole. The model suggests that the observable universe is the interior of a black hole existing within a larger parent universe. From our perspective, the Big Bang was the formation of this black hole, and from the outside, our entire cosmos would just look like a regular black hole. The size of this black hole's event horizon is defined by the Schwarzschild radius, and for a universe with the mass of ours, this radius is, interestingly, remarkably close to the radius of our observable universe. Mathematically, the singularity at the beginning of our universe is similar to the singularity at the center of a Schwarzschild black hole. The edge of our observable universe, a sphere with a diameter of 93 billion light-years, acts much like a black hole's event horizon, a boundary from which light cannot escape to an outside observer. Black holes as universe creators. Let's take this idea to its logical conclusion. If our universe was born inside a black hole, what does that imply about the estimated 100 million stellar mass black holes in our own galaxy? It suggests that each and every one could be a gateway, a seed for a new baby universe. This paints a picture of a vast cosmic ecosystem, a multiverse where universes are constantly being born. This concept, known as cosmic natural selection and explored by physicist Lee Smolin, could even offer an explanation for the fine-tuning problem, the mystery of why the fundamental constants of physics are so perfectly set for life. If universes are constantly being created, then perhaps only those whose physical laws allow for the creation of stable black holes can themselves reproduce, leading to a multiverse dominated by life-friendly universes. This theory proposes that our universe is so adept at creating black holes precisely because it was born from one, continuing an unending cosmic lineage. Smolin's theory suggests that the physical constants, like the strength of gravity or the mass of an electron, could slightly mutate with each new universe born from a bounce. Universes with constants that are better at producing black holes will have more offspring, and over countless generations these properties will become dominant. This makes the fine-tuning of our universe for life not a lucky accident but a predictable outcome of cosmic evolution on an unimaginable scale. Torsion and space-time twisting. For a universe to bounce instead of collapsing into a singularity, you need a powerful repulsive force at extreme densities. One candidate for this force comes from an extension of general relativity known as Einstein-Cartan theory. The mathematics behind this were developed in the 1920s by the brilliant French mathematician Élie Cartan. This theory incorporates a property of spacetime called torsion, which accounts for the intrinsic spin of fundamental particles. This spin is a fundamental quantum property like mass or charge that gives particles an inherent angular momentum. In standard general relativity, spacetime can bend, but it cannot twist, making the inclusion of torsion a significant modification needed for this theory to work. According to physicists like Nikodem Poplawski, at the densities found inside a black hole, the interaction between torsion and the spin of particles would create a powerful repulsive force. This torsion-induced bounce would be the mechanism that creates a new universe inside every black hole, making them not just cosmic destroyers but creators. Cosmic anisotropy. The evidence for a preferred direction in galaxy spins points to a concept called cosmic anisotropy, the idea that the universe is not the same in all directions. This directly challenges the cosmological principle, a foundational assumption in modern cosmology. This isn't just about galaxy spins. Anomalies in the cosmic microwave background radiation, first noted in data from the WMAP satellite and later confirmed by the Planck satellite, also suggest a large-scale alignment. Physicist João Magueijo famously dubbed this the axis of evil because it aligned with our solar system's plane, a result so strange it had to be a mistake, except it kept showing up with a statistical probability of being random at less than 0.1%. These anomalies, once dismissed as statistical flukes or errors in measurement, are now forcing a re-evaluation of fundamental assumptions, which is exactly how science progresses. The cosmological principle of isotropy has been a cornerstone of cosmology for nearly a century, so challenging it is met with significant scientific skepticism. However, as observational data from projects like the Sloan Digital Sky Survey and the Planck satellite becomes more precise, these persistent anomalies are becoming harder to ignore. If the universe truly does have a preferred direction, it would force us to rewrite our most basic models, and would strongly imply an origin story that involves rotation, just as the black hole universe theory predicts. From the impossible galaxies seen by JWST to the mysterious alignment of galactic spins, we are faced with observations that don't quite fit our standard story of the cosmos. The idea that our universe is inside a black hole, born from a cosmic bounce, offers a potential framework to explain these anomalies without inventing new physics. It suggests we might be part of an endless cycle of creation. What do you think? Are we living inside a black hole? Let me know your thoughts in the comments below. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Stellar Tech. Fresh observations are now shedding new light on 3I/Atlas, the massive interstellar visitor that's been puzzling astronomers since its discovery. What started as excitement over finding our third interstellar object has transformed into something far more intriguing and honestly controversial. Recent data analysis reveals patterns that just shouldn't exist in natural objects. Orbital characteristics so precise they seem almost intentional. Professor Avi Loeb and other researchers are asking uncomfortable questions. What if 3I/Atlas isn't just a comet? What if it's something designed to study us while appearing completely natural? Fresh observations reveal mysteries. Recent months of intensive observation have transformed 3I/Atlas from an exciting discovery into astronomy's most controversial object since Oumuamua. Dr. Robert Warwick from the University of Hawaii, who led the discovery team, admits that new data has revealed characteristics that challenge our understanding of natural interstellar objects. The object's behavior patterns have proven increasingly difficult to explain through conventional comet models. Advanced spectroscopic analysis by the European Southern Observatory shows surface composition anomalies that don't match any known class of solar system bodies. Most puzzling is the object's thermal signature, or rather the lack thereof. Despite approaching within 0.7 AU of the Sun, 3I/Atlas shows minimal heat emission and no detectable outgassing. Dr. Michelle Bannister from the University of Canterbury noted that objects this size should be streaming gas and dust as they heat up, but we're seeing virtually nothing. The observations have split the astronomical community between those who believe there must be a natural explanation, and others who are beginning to consider more exotic possibilities. NASA's Deep Space Network continues tracking the object, but each new measurement seems to deepen rather than resolve the mystery. The scientific debate. The astronomical community finds itself divided over 3I/Atlas, with heated debates emerging at conferences and in scientific journals. Dr. Alan Fitzsimmons from Queen's University Belfast leads the conventional camp, arguing that extraordinary claims require extraordinary evidence, and we haven't reached that threshold yet. His team maintains that unusual properties can be explained by exotic but natural compositions, possibly involving nitrogen ice or other materials rare in our solar system. However, a growing faction of researchers questions this dismissive approach. Dr. Daryl Seligman from the University of Chicago, who previously proposed natural explanations for Oumuamua, admits that 3I/Atlas presents characteristics that are harder to reconcile with known natural processes. The debate intensified when thermal modeling by Dr. Marco Michelli from the European Space Agency revealed that the object's temperature distribution doesn't match any known natural body. Spectroscopic measurements show absorption lines that appear artificially narrow, suggesting either unknown physics or manufactured materials. Dr. Sarah Seeger from MIT cautioned against rushing to conclusions, but acknowledged that we may need to expand our definitions of what constitutes natural phenomena in interstellar space. The scientific method demands skepticism, yet the mounting anomalies are forcing astronomers to confront uncomfortable possibilities. The artificial origin hypothesis. Professor Abraham Loeb, former chair of Harvard's astronomy department, has emerged as the most vocal proponent of an artificial origin for 3I/Atlas. Building on his controversial Oumuamua research, Loeb argues that the object displays technological signatures that suggest intelligent design rather than natural formation. His analysis focuses on the object's perfect orbital mechanics, unusual surface properties, and lack of expected comet behavior. Loeb's calculations suggest that 3I/Atlas's trajectory shows statistical precision that would be virtually impossible to achieve naturally. The object's approach vector, timing, and encounters with multiple planets create what he calls a reconnaissance pattern consistent with systematic exploration. In his recent paper submitted to Astrophysical Journal Letters, Loeb proposes that 3I/Atlas could be a probe designed to study our solar system while maintaining the appearance of a natural comet. His hypothesis suggests that advanced civilizations might use such camouflaged objects to observe other star systems without detection. Critics argue that Loeb is making extraordinary leaps from limited data, but his mathematical analysis of the object's properties continues to gain attention from researchers who find conventional explanations increasingly inadequate for the mounting anomalies. Unusual detection pattern. The circumstances surrounding 3I/Atlas's discovery reveal troubling patterns that suggest possible stealth capabilities. Dr. Larry Deneau from the Atlas Asteroid Survey noted that the object should have been detected 18 months earlier, based on its size and trajectory, yet it remained invisible to all automated survey systems until July 2025. The delayed detection becomes even more suspicious when considering the object's approach vector from the constellation Lynx, a region of sky that multiple survey telescopes regularly monitor. Orbital reconstruction by Dr. Davide Farnochia at NASA's Jet Propulsion Laboratory reveals that 3Y Atlas entered the outer solar system in January 2024, but somehow avoided detection despite passing through well-monitored space. The object's approach direction created additional observational challenges, as it remained positioned in areas of sky that were difficult to observe from Earth-based telescopes for extended periods. Dr. Catalina Donovan from the Linear program admitted that objects this bright should have triggered multiple detection systems, but somehow it remained hidden until practically on top of us. This pattern of avoiding detection until the last possible moment really raises questions about whether the concealment was accidental or intentional, adding weight to theories about possible artificial intelligence guiding the object's approach. Suspicious orbital characteristics. 3. I-Atlas's orbital mechanics present statistical anomalies that challenge natural origin theories through their mathematical precision. Dr. Fatih Namouni from Côte d'Azur Observatory calculated that the object's perfect alignment with the ecliptic plane has only a 0.2% probability of occurring naturally for an interstellar visitor. More striking are the object's sequential close encounters with Venus, Mars, and Jupiter, which orbital dynamicist Dr. Mattia Galeazzo from the University of Vienna determined has only a 0.005% probability of happening by chance. The precision of these encounters suggests either extraordinary coincidence or deliberate trajectory planning. 3. I-Atlas will pass within optimal observation range of each planet, maximizing potential data collection opportunities about their atmospheric compositions, magnetic fields, and moons. Dr. Alessandro Morbidelli from the Observatory of the Côte d'Azur noted that the trajectory looks almost designed to provide comprehensive reconnaissance of our solar system's major worlds. The object's velocity profile also shows subtle variations that correlate with planetary encounters, suggesting possible course corrections that natural objects shouldn't exhibit. Statistical analysis by Dr. Renu Malhotra from the University of Arizona concluded that the combined probability of all observed orbital characteristics occurring naturally is less than 0.001%, forcing serious consideration of artificial guidance systems. The hidden approach strategy. 3. I-Atlas's approach timing demonstrates what researchers are calling strategic concealment that maximizes the object's ability to study Earth while minimizing detection opportunities. Dr. Paul Wiegert from Western University discovered that the object's perihelion passage in December 2025 coincides with Earth's position in its orbit, creating an observational blind spot that has a 7% probability of occurring randomly. During this critical period, 3I Atlas will be positioned directly behind the Sun from Earth's perspective, making detailed observation extremely difficult while allowing the object unobstructed views of our planet. Celestial mechanics expert Dr. Kleomenis Tsiganis from Aristotle University noted that this timing allows the object to study Earth's electromagnetic emissions, atmospheric composition, and artificial satellite networks without interference from ground-based observations. The approach strategy becomes more sophisticated when considering that 3Y Atlas will emerge from behind the Sun in January 2026 at optimal angles for both radio telescope detection and deep space communication. Dr. Seth Shostak from the SETI Institute acknowledged that if we were designing a reconnaissance mission to study an inhabited planet, this trajectory would be nearly optimal. The implications are unsettling. 3I Atlas appears positioned to conduct comprehensive Earth observation while maintaining plausible deniability as a natural comet. Scientific opposition and evidence. Despite mounting anomalies, many astronomers maintain strong skepticism about artificial origin theories for 3I/Atlas. Dr. Alan Harris from the German Aerospace Center argues that size estimates remain uncertain, and unusual properties don't automatically imply artificial construction. His team's thermal modeling suggests the object could be significantly smaller than initial estimates, potentially explaining some observed anomalies through natural processes. Dr. Vishnu Reddy from the University of Arizona emphasizes that interstellar objects should be expected to show unusual properties, since they formed in different stellar environments with unknown conditions. Counter-evidence includes spectroscopic data showing absorption features consistent with water ice and rocky materials, though critics note these signatures could be engineered camouflage. Dr. Julie Castillo-Roges from NASA's Jet Propulsion Laboratory points out that we've only studied 3 interstellar objects, making it premature to define what constitutes normal behavior. The scientific opposition maintains that natural explanations involving exotic ices, unusual mineral compositions, or unknown formation mechanisms remain more plausible than extraterrestrial technology. Dr. Bonnie Barati from JPL advocates for continued observation rather than speculation, arguing that patience and data collection will eventually reveal natural explanations for these apparent anomalies. However, each new observation seems to strengthen rather than weaken the case for artificial origins. Ancient origins and anomalous behavior. Age analysis of 3I/Atlas reveals characteristics that seem to defy the natural aging process expected for interstellar objects. Dr. Grigory Fedoretz from Queen's University Belfast estimates the object's age at over 7 billion years based on surface composition analysis, making it older than our solar system yet showing no signs of expected cosmic weathering. Objects drifting through interstellar space for such periods should exhibit significant cosmic ray damage, micrometeorite scarring and surface oxidation, yet 3I/Atlas appears remarkably pristine. Most puzzling is the complete absence of a comet tail despite the object's approach to within 0.7 astronomical units of the Sun. Dr. Matthew Knight from the University of Maryland noted that any object containing even trace amounts of volatiles should be outgassing visibly by now, but we're seeing nothing. Structural analysis by Dr. Jean-Baptiste Vincent from the German Aerospace Center reveals density variations that are inconsistent with typical water ice spectra, suggesting either unknown materials or artificial construction. The object's rotation period of exactly 12 hours also raises suspicions, as natural bodies typically show irregular rotation rates due to impact history and gravitational perturbations. These ancient origins combined with anomalous behavior patterns continue to challenge conventional explanations. The stealth hypothesis. The concept of deliberate concealment has emerged as a serious consideration among researchers studying 3I/Atlas, potentially related to dark forest theory implications for interstellar civilizations. Dr. Liu Cixin's theoretical framework, popularized in science fiction but based on real game theory, suggests that advanced civilizations might prefer stealth over open contact to avoid potential threats. Professor Avi Loeb proposes that 3I/Atlas represents what he calls archaeological reconnaissance, a method for studying planetary systems while maintaining the cover of natural phenomena. This hypothesis explains why the object exhibits just enough anomalous behavior to suggest artificiality to careful observers while maintaining plausible deniability as a natural comet. Dr. Jacob Haq Misra from the Blue Marble Space Institute has studied the implications of such stealth strategies, noting that advanced civilizations might prefer observation over contact to minimize risks while gathering intelligence about other worlds. The stealth hypothesis suggests that 3I/Atlas could be collecting data about Earth's technological level, atmospheric composition, and artificial electromagnetic signatures while appearing to be a routine interstellar visitor. Radio telescope monitoring by Dr. Sophia Sheikh at the SETI Institute has detected no obvious artificial signals, but sophisticated probes might use communication methods undetectable by current technology or transmit data during periods when Earth-based observations are impossible. Lessons from Oumuamua. The scientific community's handling of Oumuamua in 2017 provides crucial context for evaluating 3I/Atlas and the importance of maintaining open-minded investigation. Dr. Robert Warwick, who discovered both objects, admits that we missed significant opportunities with Oumuamua by dismissing anomalies too quickly rather than pursuing thorough investigation. The 2017 visitor exhibited unexplained acceleration, unusual reflectivity, and extreme elongation that were initially attributed to natural causes without adequate investigation. Professor Abraham Loeb's controversial artificial origin hypothesis for Oumuamua was largely dismissed by the astronomical establishment, yet alternative natural explanations have proven increasingly problematic under scrutiny. Dr. Daryl Seligman's hydrogen iceberg theory requires formation conditions so exotic they approach the implausible, highlighting the difficulty of finding natural explanations for truly anomalous objects. 3I/Atlas represents a second chance to properly investigate an interstellar visitor with advanced instruments and sufficient observation time. Dr. Thomas Zurbuchen, former NASA Associate Administrator, emphasized that extraordinary phenomena deserve extraordinary investigation, not extraordinary dismissal. The lesson from Oumuamua is clear. When faced with genuinely anomalous objects, the scientific community must resist the temptation to force natural explanations and instead pursue comprehensive investigation that considers all possibilities, including those that challenge our current understanding of what's possible in the universe. 3i/Atlas continues its journey through our solar system, carrying secrets that may fundamentally challenge our understanding of what travels between the stars. Whether it's an exotic natural phenomenon or something more extraordinary, this mysterious visitor has already forced astronomers to confront uncomfortable questions about the universe around us. The patterns are too precise, the timing too convenient, and the behavior too strange to dismiss easily. Subscribe to Stellar Tech for more investigations into cosmic mysteries that blur the line between natural phenomena and something far more intriguing. It started as nothing more than a flicker in the data, a cold, silent speck moving far faster than anything that should have been out there. But then, the James Webb Space Telescope captured the first real image of 3i Atlas, confirming its presence and reigniting debates about its origin. Now traveling at 152,000 miles per hour from the depths of interstellar space, this mysterious visitor is rewriting what we know about cosmic travelers. The flicker in the data. The flicker in data that led to the discovery of 3i Atlas was first noticed by astronomer Larry Deneau using the Atlas survey system in early 2025. Initially, the object appeared as a faint point source barely distinguishable from background noise, traveling at an extraordinary speed that defied expectations. Rapid follow-up observations from telescopes worldwide confirmed its hyperbolic trajectory, indicating an interstellar origin beyond our solar system. The discovery highlighted the increasing capability of modern automated sky surveys and the importance of advanced image processing techniques in spotting elusive cosmic phenomena. 3i Atlas's initial data sparked excitement and mystery in equal measure, leading to widespread international scientific collaboration to understand its true nature. The detection demonstrated the effectiveness of coordinated astronomy projects working in concert across hemispheres to capture fleeting interstellar visitors. What began as a mere computational anomaly quickly evolved into one of the most significant astronomical discoveries of the decade, challenging our understanding of what travels through the void between stars and forcing scientists to reconsider fundamental assumptions about interstellar objects. 152,000 mph from the void. Moving at an incredible velocity of approximately 152,000 miles per hour, 3i Atlas stands as one of the fastest objects ever recorded within our solar system's boundaries. Its extraordinary speed distinguishes it from typical asteroids or comets native to our cosmic neighborhood, definitively confirming its extragalactic origins. The precise velocity measurements were obtained using combined data from the Hubble Space Telescope and ground-based observatories worldwide. This phenomenal speed suggests a trajectory completely uninfluenced by our sun's gravitational pull, affirming that 3i Atlas is truly a visitor from another star system. Scientists involved in tracking the object, including Dr. Davide Farnocchia at NASA's Jet Propulsion Laboratory, are racing against time to gather detailed observations before it disappears forever into the cosmic void. The object's rapid passage through our observational field poses unprecedented challenges for data collection, requiring lightning-fast coordination among observatories globally to maximize information retrieval during its brief transit. Such extraordinary velocity raises fundamental questions about the forces that accelerated this object to such speeds and whether natural processes alone could account for its remarkable journey through interstellar space. 3 visitors, 7 years. Over the span of 7 years, humanity has documented the arrival of 3 confirmed interstellar visitors: Oumuamua in 2017, 2i Borisov in 2019, and now 3i Atlas in 2025. Each visitor has brought unique characteristics that challenge our understanding of interstellar objects and their origins. Oumuamua puzzled scientists with its cigar-like shape and unexplained acceleration, while 2i Borisov displayed traditional comet behavior with visible outgassing. 3i Atlas represents perhaps the most enigmatic of the 3, combining unprecedented size with unusual physical properties. The increasing frequency of these detections suggests either improved observational capabilities or a genuine increase in interstellar traffic through our solar system. Dr. Alan Fitzsimmons from Queen's University Belfast notes that statistical models predicted we should encounter one interstellar object every few years, yet the diversity among our 3 visitors exceeds all theoretical expectations. This pattern has prompted astronomers to reconsider whether we're witnessing random cosmic wanderers or something more systematic. The progression from Oumuamua's mysteries to 3I Atlas's apparent technological signatures suggests an escalating complexity that challenges conventional explanations for these cosmic visitors. James Webb's metallic discovery. Despite its immense size, 3I/Atlas exhibits distinctly metallic characteristics not commonly observed in natural celestial bodies traveling through space. Recently, the James Webb Space Telescope captured unprecedented infrared images revealing highly reflective surfaces and spectral signatures indicative of engineered materials rather than typical rocky or icy compositions. Dr. Jane Rigby from the Space Telescope Science Institute leads the comprehensive analysis of these groundbreaking findings that challenge conventional understanding of interstellar objects. The spacecraft's sophisticated instruments detected unusual heat emission patterns consistent with metallic alloys and composite materials rather than the typical signatures expected from cometary ices or rocky asteroids. These observations fundamentally challenge conventional cometary models and provide compelling evidence supporting theories about the object's potential artificial origin. The metallic properties suggest advanced engineering capabilities far beyond current human technology, with surface materials that appear designed to withstand the harsh conditions of interstellar space. The discovery has prompted intense international collaboration, as scientists attempt to understand how such materials could survive millions of years of cosmic radiation and micrometeorite bombardment during the object's journey between star systems. The machine that steers itself. Detailed tracking of 3I/Atlas reveals subtle but unmistakable evidence that it actively maneuvers through space, strongly suggesting the presence of an autonomous guidance system. Dr. Amir Siraj from Harvard University highlights observational data showing minute trajectory corrections that cannot be explained by gravitational influences or solar radiation pressure alone. These course adjustments occur with mathematical precision, indicating sophisticated onboard navigation capabilities. Experts hypothesize the presence of an advanced propulsion mechanism or intelligent navigation system actively controlling the object's path through our solar system. Such self-steering capability would represent a technological achievement far beyond anything in humanity's current arsenal, suggesting engineering by a civilization with capabilities we can barely comprehend. The subtle nature of these adjustments indicates a system designed for stealth and efficiency, rather than dramatic maneuvers. Analysis suggests the object may be following a predetermined flight path, possibly executing a systematic survey of our solar system's major bodies. This revelation intensifies scientific debates about whether 3I/Atlas represents a natural interstellar object, or an intelligently designed probe conducting reconnaissance of our cosmic neighborhood, with sophisticated artificial intelligence guiding its every movement. Information blackout. In recent months, astronomical observations of 3I/Atlas have been plagued by mysterious communication disruptions that some scientists describe as an emerging information blackout. Data streams from major observatories occasionally suffer unexplained interruptions, creating frustrating gaps in the continuous monitoring required for comprehensive analysis. Dr. Sarah Seeger from the Massachusetts Institute of Technology warns that these systematic blackouts are hindering critical data collection during the object's closest approach to Earth. The disruptions appear to follow patterns that cannot be attributed to equipment failures or atmospheric conditions, leading to speculation that the object may employ active measures to obscure detailed observation. Information loss challenges astronomers to devise innovative observational strategies and backup systems to maintain contact during the object's rapid transit. Some researchers theorize that 3I/Atlas possesses adaptive countermeasures designed to limit scrutiny from potential observers. The timing of these blackouts often coincides with moments when the most sensitive instruments would normally capture their highest quality data. This phenomenon has prompted the development of new redundant observation networks and the deployment of multiple independent systems to circumvent whatever mechanism might be causing these mysterious data interruptions. Adaptive shielding technology. Scientists, have developed theories suggesting that 3I/Atlas employs some kind of sophisticated adaptive shielding technology to survive the extreme conditions of interstellar space over, potentially millions of years. Dr. Monica Grady from the Open University explains that such advanced shielding systems might dynamically protect the object from cosmic radiation, solar particle streams, and micrometeorite impacts while maintaining its structural integrity. Evidence from variable brightness patterns and sophisticated thermal management systems supports this revolutionary hypothesis about the object's survival mechanisms. Now, these adaptive shields would enable prolonged operational capability during close stellar encounters, making the object far more than just a simple interstellar comet. If this theoretical technology is confirmed through continued observation, it would, quite frankly, fundamentally revolutionize human understanding of materials science and extraterrestrial engineering capabilities. The shielding appears to respond to environmental changes, adjusting its properties based on local radiation levels and particle densities. Such technology, it would require advanced sensors and automated response systems working in perfect coordination. The implications extend far beyond just academic interest, suggesting that 3I/Atlas represents an engineering achievement that could provide blueprints for humanity's own future interstellar missions. Understanding these protective mechanisms could unlock secrets essential for our survival during extended journeys between star systems. The Ancient Probe Network. So, recent theoretical frameworks propose that 3I/Atlas represents a component of an ancient probe network designed to systematically explore and monitor galactic environments across vast timescales. Dr. Frank Drake, founder of modern SETI research, has discussed the possibility of coordinated reconnaissance systems deployed by advanced civilizations to study emerging planetary systems throughout the galaxy. These theoretical probes might maintain communication through quantum entanglement or, other exotic mechanisms currently beyond human technological comprehension. Evidence suggests such a network could have been deployed millions or even billions of years ago by a highly advanced civilization with capabilities spanning galactic distances. The probes would operate with extreme longevity, possibly self-repairing and adapting to changing cosmic conditions over geological timescales. Exploring 3I/Atlas might offer unprecedented insights into this enigmatic interstellar monitoring system and reveal the intentions of its creators. The network hypothesis explains the increasing frequency of interstellar visitors and their apparent technological sophistication. Such a system would represent the ultimate expression of scientific curiosity and technological achievement, allowing a civilization to study the development of life and intelligence across thousands of star systems simultaneously, while, remaining largely undetected until their technology is sufficiently advanced for meaningful contact. Prime numbers in heat signatures. Scientists analyzing thermal emissions from 3I/Atlas have detected periodic fluctuations that correspond remarkably to prime number sequences, creating patterns unlikely to arise from any known natural process. Dr. Seth Shostak from the SETI Institute emphasizes that such mathematical precision in thermal signatures strongly indicates intentional signaling by an intelligent source rather than random physical phenomena. The presence of prime-numbered cycles in heat emissions represents a form of universal mathematical communication that any technologically advanced civilization would recognize. These observations add compelling evidence to theories that 3I/Atlas harbors sophisticated technological features specifically implemented to communicate or encode information for other intelligences. The mathematical precision of these thermal patterns suggests deliberate design rather than coincidental physical processes. Researchers are working to decode these numerical sequences, hoping they might contain more complex information about the object's origins or mission. The use of prime numbers as a communication method demonstrates sophisticated understanding of mathematics as a universal language. This discovery represents potentially the first confirmed technological signal from an extraterrestrial source, marking a watershed moment in humanity's search for cosmic intelligence and fundamentally altering our understanding of our place in the universe. We were never the observers. The accumulating evidence surrounding 3I/Atlas fundamentally challenges humanity's assumption that we are the primary observers of cosmic phenomena. Dr. Avi Loeb from Harvard University argues that this interstellar visitor demonstrates clear evidence of extraterrestrial intelligence actively monitoring and studying planetary systems throughout the galaxy. Observational data suggests these cosmic visitors are neither passive wanderers nor accidental tourists, but may represent fundamentally proactive agents in galactic scientific endeavors. This paradigm shift forces humanity to reconsider our place in the cosmic hierarchy and acknowledge the possibility that we have been subjects of study rather than the sole investigators. The revelation that advanced civilizations may have been observing Earth for extended periods alters philosophical and scientific perspectives about human uniqueness and cosmic significance. The systematic nature of these visits suggests a level of galactic organization and scientific methodology that honestly dwarfs human capabilities. Recognition that we may have always been monitored by superior intelligences challenges anthropocentric worldviews and demands humility in our cosmic perspective. This discovery marks the beginning of humanity's true integration into a galaxy populated by intelligence far exceeding our own technological and scientific achievements. The remarkable data captured by the James Webb Space Telescope has propelled humanity into a new era of cosmic discovery and understanding. As the secrets of 3I/Atlas continue to unfold, we find ourselves confronting the profound possibility that we are not alone in the universe. The ongoing study of this extraordinary visitor challenges our fundamental notions of life, technology, and our place in the cosmos. Stay with Stellar Tech as we continue following these groundbreaking developments, seeking truth among the stars, and preparing for humanity's next chapter in cosmic exploration. What if a rocket intercepted a messenger from another star? Recently, the internet exploded with claims that a Falcon 9 rocket spotted something moving on the surface of 3I/Atlas, an interstellar comet older than our own sun. But what's the real story behind this cosmic visitor and the rumors of its interception? The truth is more fascinating than the fiction, revealing the incredible challenges and profound possibilities of chasing these messengers from distant star systems. Let's explore this together. What makes 3I/Atlas special? So what's the big deal with this specific comet? Imagine a visitor from a completely different neighborhood, one that holds clues to how other solar systems are built. 3I/Atlas isn't just another space rock. It's a pristine sample of an entirely different stellar environment. It was discovered on July 1, 2025, by the Atlas Survey in Chile, a project co-led by astronomer Larry Deneau. That system is designed to spot near-Earth objects, so finding an interstellar guest is a testament to its incredible reach. Astronomers quickly confirmed its hyperbolic trajectory, the telltale sign of an interstellar origin. This object is racing through our solar system at a staggering 58 to 61 kilometers per second. To put that in perspective, you could travel from the Earth to the Moon in a little over 6 hours at that speed. Scientists estimate it could be up to 7 billion years old, predating our Sun. This means it carries a chemical record from an earlier epoch of the Milky Way galaxy. What truly makes it a scientific treasure is its composition. Observations from the Hubble and James Webb Space Telescopes show it's a true comet, complete with a dusty coma and tail carrying water ice, organic molecules, and silicate dust from its home star. The Falcon 9 connection debunked. Here's where the story gets twisted. Did a SpaceX rocket really intercept this interstellar traveler? The claim went viral, fueled by a public fascination with SpaceX's capabilities. But the reality is far more routine. Let's look at the facts. On August 18, 2025, a Falcon 9 rocket did launch from Vandenberg Space Force Base in California. However, its mission, overseen by figures like SpaceX's CEO Elon Musk, was to deploy 24 Starlink satellites into a low-Earth polar orbit. This was a milestone for sure, but entirely unrelated to the comet. There has been no spacecraft from SpaceX or any other agency that has intercepted or interacted with 3I/Atlas. These kinds of rumors spread easily because they blend a known, dynamic entity like SpaceX with a mysterious celestial event. It's a compelling narrative, but it's pure fiction. The scale of an Earth orbit satellite deployment versus a deep space, high-speed intercept mission is colossal. Furthermore, space agencies are incredibly public about their scientific missions. An operation of this magnitude would be nearly impossible to hide from the global network of professional and amateur astronomers who constantly monitor the skies. The truth is, all Falcon 9 launches in that period were for planned payloads into Earth's orbit. The physics of interception. So, why couldn't we just send a Falcon 9 to check it out? The math is sobering. As physicist Andreas Hein of the Initiative for Interstellar Studies has detailed in mission concepts like Project Lyra, chasing an object moving at over 200,000 kilometers per hour is a monumental challenge. By the time 3I Atlas was identified, it was already hurtling outwards at immense speed. To even attempt a direct flyby, a spacecraft would need an epic velocity change. A Falcon 9 is a workhorse for lifting heavy loads, but it's not designed for the extreme velocity needed in deep space. You'd need a specialized and powerful kick stage that fires after the main rocket has done its job, pushing a small probe to incredible speeds. Even then, the launch window is punishingly narrow. Miss it by a few weeks, and the target is simply too far away and moving too fast to ever catch. Even our fastest spacecraft only achieve their speeds by falling towards the sun. To catch 3I Atlas, we would need a mission planned years in advance, likely involving a massive rocket and complex gravity assists, a luxury we simply don't have with these surprise visitors. Alien chemistry possibilities. This is where the science gets really exciting. What if this comet is carrying chemicals we've never seen before? Astrobiologists like Sarah Seeger at MIT spend their careers considering such possibilities. At an estimated 7 billion years old, 3I Atlas formed in a stellar environment that was likely very different from our own. The water, ice, and organic molecules detected might have structures fundamentally alien to our solar system's chemistry. This opens the door to a profound question related to panspermia, the idea that the chemical seeds of life are spread throughout space by objects like comets. Even more fascinating is the idea of chirality. On Earth, life uses what we call left-handed amino acids. There's no known chemical reason for this preference. Finding the opposite right-handed amino acids on 3I Atlas would be a monumental discovery. It would be powerful evidence for an independent origin of life's building blocks elsewhere in the galaxy. It would be like finding a recipe card written in a language that doesn't exist on our planet, profoundly impacting our search for life beyond Earth, and hinting that the universe is far more creative with its chemistry than we ever imagined. 3 missed opportunities. We're facing a pattern that is becoming painfully clear. In less than a decade, 3 confirmed interstellar visitors have sailed right past us. First, in 2017, came one Oumuamua. This bizarre object baffled astronomers. It showed no visible coma, yet it was accelerating away from the sun, a mystery that led Harvard astronomer Avi Loeb to famously propose it could be an artifact of extraterrestrial technology. By the time we spotted it, it was already leaving. Then, in 2019, 2I Borisov appeared. This one was clearly a comet, giving us our first real look at the chemistry of another solar system. Studies showed it had an unusually high concentration of carbon monoxide, a tantalizing clue that it formed in a very different, very cold environment, but without a sample, it remains a distant observation. Now we have 3I Atlas in 2025, our third confirmed cosmic messenger. It represents another missed chance for a close-up look. 3 unique opportunities, each with its own fascinating mysteries, and 3 misses. It raises the urgent question of how many more cosmic messengers we will simply let fly by while we remain stuck on the sidelines. Future intercept technology. So, are we doomed to just watch from the sidelines forever? Not necessarily. Imagine a spacecraft parked in space, just waiting. That's the core idea behind the European Space Agency's Comet Interceptor mission. Led by principal investigator Geraint Jones. Planned for launch in 2029, this innovative spacecraft won't have a predetermined target. Instead, it will travel to the Sun-Earth L2 Lagrange point, a gravitationally stable spot about 1.5 million kilometers from Earth, and wait. It will lie dormant until astronomers spot a new interstellar object with enough lead time. Once a target is selected, Comet Interceptor will begin the chase. It's 3 spacecraft in one. It will release 2 smaller probes to fly through the comet's coma from different angles, creating a 3D profile of its nucleus and surrounding environment. This isn't the only idea on the table. Some scientists at NASA have proposed concepts for rapid response missions. The goal is to move from passive observation to active pursuit, finally giving us the ability to reach out and touch one of these cosmic travelers. Scientific implications. What if we did manage to grab a piece of another star system? The implications would be, well, just transformative. As cosmochemist Connell Alexander has shown by studying meteorites, analyzing pristine material can totally revolutionize our understanding of solar system formation. Now just imagine doing that for another star. The primary goal here would be to analyze a pristine sample of matter from beyond our solar system. A key technique would be analyzing its isotopic ratios. Isotopes are variants of elements with different numbers of neutrons, and their ratios act like a fingerprint of the stellar nursery where the object formed. This could tell us if it originated in a region rich with the remnants of supernovas, for example. Furthermore, studying its trajectory with extreme precision could reveal subtle secrets. Tiny, unexplained deviations from its path could hint at unknown gravitational effects. And perhaps most compellingly, if we find complex organic molecules, it would really fuel the panspermia hypothesis, suggesting that the building blocks of life are constantly traveling between star systems. We might be looking right at revolutionary chemistry without even recognizing it. Trajectory analysis and mysteries. Let's dig into the path of this cosmic wanderer. The hyperbolic trajectory of 3I Atlas is the smoking gun that proves it's not from around here. Its path is an open curve, meaning it will swing around the sun once and then exit back into interstellar space, never to return. Its high hyperbolic excess velocity, the speed it retains after escaping the sun's gravity, is a key indicator. For 3I Atlas, this speed is around 58 kilometers per second. The object makes its closest approach to the sun on October 30th, 2025, at a distance of about 1.4 astronomical units. One of the biggest mysteries, a puzzle that astronomers like Bill Gray have spent years trying to solve for various objects, is its origin. Astronomers use powerful software to run the comet's trajectory backward in time, checking against star catalogs to see if its path aligns with any known star systems it might have passed millions of years ago. So far, no definitive origin star has been found for any interstellar object. They appear to be true wanderers, ejected from their home systems long ago, and drifting through the void for potentially billions of years. The official facts. So, let's separate fact from fiction and lay out what scientists have officially confirmed. 3I Atlas was first detected on July 1, 2025, by the Atlas survey in Chile. The 3I in its name literally means it's the third confirmed interstellar object. Within a day, its hyperbolic trajectory was confirmed by observatories around the world. As leading interstellar object expert Karen Meach has noted, the global coordination to observe these targets is incredible. It is traveling at a velocity of roughly 58 to 61 kilometers per second relative to the Sun. Hubble Space Telescope images from July 2025 revealed a dusty coma surrounding the nucleus. Spectroscopic analysis by both Hubble and the James Webb Space Telescope confirmed the presence of water ice, organic molecules, carbon dioxide, and silicate dust. NASA has officially stated that the object poses no danger to Earth, always remaining more than 150 million miles away. And to be perfectly clear, despite the viral rumors, no spacecraft, including any Falcon 9, has intercepted or is planned to intercept 3I Atlas. All SpaceX launches around that time were for routine satellite deployments. The bigger picture. In the end, the frenzy over a Falcon 9 intercepting 3I Atlas, while factually wrong, highlights a much deeper truth. Humanity is captivated by the idea of reaching out to these cosmic messengers. We've now seen 3 of these objects in just a few years, suggesting they may be common visitors. With projects like the Vera C. Rubin Observatory coming online, our ability to detect them will only increase. This isn't just a scientific question anymore, it's a strategic one. This connects directly to the Fermi paradox, a question famously championed by SETI astronomer Jill Tarter. If the universe is vast and the building blocks for life are being delivered across the galaxy like cosmic seeds, then where is everybody? Do we invest in developing a permanent, ready-to-launch intercept mission? The technology exists, but it requires political will and financial commitment. The decisions we make now will determine if, next time, we are ready to capture one of these cosmic opportunities, or if we will once again watch it disappear into the void, taking its secrets with it. The universe is constantly sending us messages, written in the language of chemistry and physics, carried on messengers like 3I Atlas. While we weren't ready this time, the future of interstellar interception is closer than you think. What secrets will the next visitor reveal, and will we be there to unlock them? If you want to be here for that next great discovery, make sure you're subscribed to Stellar Tech as we continue to explore the biggest mysteries on the edge of the galaxy. Don't forget to like, subscribe, and hit the bell icon. Thanks for watching.